Okay, section 2.2.1, we're going to talk about density curves. Take a look at the objectives. So we're going to estimate the relative locations of median and mean on a density curve. We'll use the 68, 95, 99.7 rule to estimate areas in a normal distribution. And we'll use table A or technology to find the proportion of z values in a specified interval, or a z-score from a percentile in the standard normal distribution. So a lot of words we haven't necessarily learned yet, but will as we go. All right, just a note on how we explore quantitative data to this point. First of all, always plot your data. So you're going to make a graph, usually a dot plot or a stem plot or a histogram. We're going to look for overall patterns. So that's the shape center spread and any striking departures. So any outliers, and we now have the 1.5 times the IQR rule for outliers. We'll calculate numerical summaries to briefly describe center and spread. And then lastly, when the overall pattern of a large number of observation is very regularly, we can describe it by a smooth curve. And that's what a density curve is. So a density curve has these two characteristics that are extremely important. One, it's always on or above the horizontal axis. And two, it has an area of exactly 1 underneath it. And the way that can be achieved is by, you remember that the scale of the y-axis doesn't matter. It can be frequency, it can be relative frequency. That's not going to change the overall shape of your histogram. So you can scale it in such a way that if you added up all the areas of your rectangles, they would add up to exactly 1. And in that sense, the density curve having an area of exactly 1 underneath it, then anytime we find an area on an interval, that area will represent the proportion of individuals that fall within that interval, okay? So this is an example of 947th grade students in Gary, Indiana, and their scores on the vocabulary part of the Iowa test of basic skills, right? So whatever that percent is that I shaded there would represent the percent of students that got the scores on that interval. So let's pretend that that's maybe 15%. And I'll say that this is, let's say I stopped at like 4.5. Then I could say that 15% of those students scored between 2 and 4.5 on the vocabulary part of the Iowa test of basic skills. Okay? And so, as we said, the total area is 1, and that represents 100% of the data. All right, some distinguishing features of the density curve. The median is the equal areas point. So that's the point that divides the area exactly in half. And the mean is the balance point. So that's the point at which, if you were to cut the density curve out of solid material, you would be able to balance it on the mean. So if the curve is symmetric, the mean and the median will be the same, right in the center. If it's skewed, the mean is going to be pulled away from the median in the direction of the long tail. Okay, and we already kind of had an idea about this. The mean is not a resistant measure. It gets pulled towards that skew. All right, so here's an example where the red triangle is centered under the mean. In the symmetric example, the mean and the median are the same, meaning the balance point is the same as the equal areas point. In the skewed distribution, the median remains closer to this peak, and the mean gets pulled in the direction of the skew. So a density curve is really an idealized version of an idealized description of a distribution of data. Remember that it has exactly an area of 1 underneath it. I'm going to start using some more notation. We've already been doing this, but the mean we usually represent with mu. The standard deviation of a density curve will represent with sigma. All right, so normal distributions are just special kinds of density curves that happen to come up quite a bit in statistics, and we'll explore why. But for now, here's what you need to know about them. It's a proper noun, so it's capital N normal distributions. And they all have the same shape, which are they are symmetric, single peaked, and bell-shaped. They may be flatter or taller, but they all have those rough characteristics. We say that it's completely described by giving its mean and standard deviation. Sometimes you'll see this notation where it's a capital N, mu, comma, sigma, but they'll actually write in the numbers for mu and sigma, and it's just understood that the first one is the mean and the second one is the standard deviation. When we say completely described, what we mean is that all you would have to give us is the mean and standard deviation, and that's enough information to mathematically graph that specific normal distribution. Okay. A couple of things. The mean will be right in the center. A standard deviation can be eyeballed by looking for the point of inflection. So if you were in calculus with me last year, you'll know what I mean by that. If you were not, I can explain it real quick. So we have this thing called concavity, which is kind of which way the curve is facing, right? That's concave down. Concave down like a frown. This is concave up like a cup. There's a point at which the concavity changes there. So it's right about here. That's called the inflection point. You can eyeball where that inflection point is and trace it down vertically to the x-axis, the horizontal axis. The distance from the mean to where that inflection point is going to be 1 standard deviation, right? And then from there, now you have that measurement, so I would know that that same distance is a 2nd standard deviation. And so on. So if it's skinnier, the standard deviation is going to be smaller because that inflection point is going to be closer to the mean. All right, so let's do an example. According to the CDC, the heights of 12-year-olds males are approximately normally distributed with a mean of 149 centimeters and a standard deviation of 9 centimeters. Sketch the distribution, label the mean and the points 1, 2, and 3 standard deviations from the mean. Okay. So here we go. The given information, it's a normal distribution with a mean of 149 centimeters and a standard deviation of 9 centimeters. All right. So this is 12-year-old male heights. Always need to label our diagrams, and I'm going to say it's in centimeters. Okay, so that's 149. This is a pretty rough sketch, but I'm going to go, all right, let's say my point of inflection is right about there. The standard deviation they said is 9, so 149 plus 9 is 158. That's one standard deviation. I'll then eyeball that same distance. It's 167. Eyeball that same distance. That's 176. And then let's do to the left as well. 140. 131. 122. All right, that's it. Okay, so more about normal distributions. Remember that any unique normal distribution is completely specified by its mean and its standard deviation. The mean is in the center of the what we call the normal curve. The standard deviation is the distance from the center to the change of curvature. Remember, that's what we call points of inflection. And then we can abbreviate the normal distribution with mean, mu, and standard deviation, sigma, as capital N, parentheses, mu, comma, sigma. All right, now we get the 68, 95, 99.7 rule. If there's one thing about mathematicians and statisticians, it's that their naming conventions are pretty direct. So 68, 95, 99.7 is the approximate proportion of data that falls within 1, 2, then 3 standard deviations respectively. Meaning approximately 68% of your observations will fall within 1 standard deviation of the mean. 95% will fall within 2 standard deviations of the mean, and 99.7%, so almost all the data, is within 3 standard deviations of the mean. When I say 1 standard deviation, I mean to each side. So you can see in this diagram, this is 1 standard deviation to each side. That represents 68% of the data. Then we have 2 standard deviations, then 3 standard deviations. Using the earlier example about what percentage of 12-year-old boys will be over 158 centimeters tall. Over 158 centimeters, I'm looking at, there's 158 centimeters, right? I want to know what percentage of them are over 158. So that's this area represents the percent that are over 158. All right, so I can use that 68, 95, 99.7 rule. And I notice that 158 is 1 standard deviation to the right. So if I come over here and I go 1 standard deviation to the left, the area in here represents 68% of our observations, right? And since normal distributions are symmetric, I can expect that the tails are going to have the remaining area in them. So both tails together are going to then have to represent 100 minus that 68. Great, that's 32. So I know that both tails together have 32% of the data, but I only want the tail that's above 158. Since they're symmetric, they should have the same amount in each, so I can just divide this by 2. And there we go. My answer is 16. There's 16% of 12-year-old males that are above 158 centimeters. About what percentage of 12-year-old boys will be between 131 and 140 centimeters tall? All right, so let's go back. Let's see, can I back out my work enough here? Great. So I'm looking for between 131 and 140. So let's see, 131 here and 140 here, right? All right, there's a couple ways you can do this. Let's see, what's the easiest? Well, so we're looking for that area. And one thing I'll say is that since 140 is only one standard deviation, just based on the last problem we did, if I just pay attention to this area, I know that that is 16%, right? All right. Now, what I want to do is take off this area. So I'm going to subtract off whatever that red area is. So to figure out what that red area is, that's 2 standard deviations away. So remember that 2 standard deviations at 68 encompassed in here is 95% of the data. So this is from my pink boundary to my other pink boundary, which means outside, there's only 5% of the data remaining, right? Here to here. So that's a total of 5% of the data. 5 divided by 2 gives me 2.5%. So each of these tails is 2.5%. So that's what I'm looking to subtract off of my 16%, which is then going to leave me with just 13.5%. All right, so in that green shaded area, that's 13.5% of my data. So "13.5% of 12-year-old boys will be between 131 and 140 centimeters tall." All right, let's look at another example here. Suppose the distribution of test scores is approximately normal. In the middle, 95% of these scores are between 72 and 84. What are the mean and standard deviation of this distribution? All right, so let's draw this out as best we can. Oh, that was not a good one. It's a little better. All right, so I know that the mean will be in the center here. We know they state that it's a normal distribution, so, but they give me 2 standard deviations away, right? Oh no, I'm sorry, they give us 95% fall between those 2 scores. And since we have that 68, 95, 99.7 rule for normal distributions, we know that those numbers they're talking about are 2 standard deviations away. So this will be 84. Then I'll eyeball this. 1, 2. This will be 72. Okay, well, since it's symmetric, you know that the mean has to be exactly in the middle of those 2. So we can just find the mean of those 2 numbers. That gives us 78. So now I know my mean is 78. And I just need my standard deviation. Well, this is 2 standard deviations away from my mean. So all I need to do is find that total distance and divide it by 2. and that should be my standard deviation, right? So to find the distance between 2 points on a number line, you subtract larger minus smaller. Give me 6. And then since that's 2 standard deviations, I'll divide it by 2, and sigma equals 3. So it's normal with a mean of 78 and a standard deviation of 3. And you could fill in the in-between if you like, right? This will be 81. This will be 75. All right, can we calculate the percent of scores that are above 80 and explain? Not precisely. Because 80 does not fall on a whole number of standard deviations. Right? If it was 81, we could do it because that's one standard deviation above the mean. And we already did a problem like this where we found out that the area in that tail is 16%. So we know that it's going to be more than 16% of the scores, but we don't know how much more yet. We will be able to do that. All right, let's do an example. So the histogram below shows the distribution of batting average for the 432 Major League Baseball players with at least 100 plate appearances in a recent season. The smooth curve shows the overall shape of the distribution. Remember that it's an idealization of the histogram and that it has a total area of 1. Whoops, meaning 100% as a proportion of the data. In the first graph below, the bars in red represent the proportion of players who had batting averages of at least 270. So that red shaded area is at least 270 or above. And there are 177 such players out of 432 for a proportion of 0.410. So that's 41%. And the second graph, the area under the curve to the right of 270 is shaded. This area is 391, which is only about 0.019 away from the actual proportion of 41%. So what we're illustrating here is that, remember, the density curve is an idealization, but it gets us very close to the true proportions that we're looking for. All right, so in the previous alternate example about Major League Baseball players, the mean of 432 batting averages was 0.261 with a standard deviation of 0.034. Suppose that the distribution is exactly normal with those same mean and standard deviation. A, sketch a normal density curve. Label the points that are 1, 2, and 3 standard deviations from the mean. And then B, what percent of batting averages were above 329. And C, what percent of the batting averages are between 193 and 295. Okay, so let's get to sketching. Oh, I can do better than that. Hold on. It's hard to do on the iPad. Oh boy. No. I'm pausing it till I get a good one. Okay, this one has to do. All right, so the mean is 261. Normal, we have a mean of 261. We have a standard deviation of all right, we want to kind of eyeball where that point of inflection is. Right about there. There's my standard deviation. 2 standard deviations. 3 standard deviations. So I'm going to just add that standard deviation of 0.034. So 0.261 plus 0.034, 0.295 plus 0.034, 0.329 plus 0.0234, 0.363. And then on the other side, I'll subtract. Oh, that's not far enough. 261 minus 0.034. That's 0.277. That's 0.193. That's 0.159. All right, so that's part A. Part B, what percent of the averages are above 0.329? We'll shade what they're looking for. Notice that 0.329 is 2 standard deviations above the mean. And so using the 68, 95, 99.7 rule, we know that in this enclosed area is 95% of the data, meaning there's 5% left total in the tails, meaning there's 2.5% in one tail. All right, so our answer to B is 2.5%. What percent of the batting averages are between 193 and 295? All right. So all right, so we're looking for this total area. Well, here between the greens is 68% of the data. So we need to add onto this how much is in here. Well, 2 standard deviations is 95% of the data, so that would be from here to here. It would be all the pink area. So if I do just the 95 minus the 68, so 0.95 minus the 68, 0.68, that's 27. And that's telling me what would be left in total in both these chunks, right? So that's 20, that's 0.27. But I only need to add on one of those. So we're going to divide that 27 by 2. 0.27 divided by 2 is 0.135. All right, so the area that I'm finding, remember, is this plus the 68. So I'll have 0.68 plus 0.135. And that gets me 0.815. And they ask, what percent? Show your work, so our answer is 81.5%. All right. Go ahead and pause it here. Here's a little student example for you. We'll go over it in our next class. Good luck.